So we are finally ready to start a new chapter. And not only is it a new chapter, I mean, when we went from chapter 2 to chapter 3, we still did parabolas because we went from focusing on the vertex to focusing on the x-intercepts. This one is a new chapter. Our chapter is called Polynomials. So I am interested if anyone could give me an example of we don't need another example. Okay, so our polynomial is a series of, it's called terms, that are added and subtracted together. And the terms start with, so we have up here like an x. If you just have x, that means it's x to the 1. And we have x squared, x to the 2. You could do x to the 3, x to the 4. What you cannot do with a polynomial is like the square root of x. Can't. That does not make a polynomial. You cannot do 1 over an x. That does not make a polynomial. And then the third one that doesn't would be like if we did 5 to the x. Okay, they have to be an x to the integer power. Now, what about let me get rid of these 3 examples. This right here is also a polynomial. 3. Well, that doesn't have an x, but it really does because that's really 3x to the 0. Because anything to the 0 is multiplying by 1. So this counts as 3 times 1. So really, when I make my list here, you're starting with x to the 0 and then going down from there. Let's say you have a polynomial of just one term. We'll just call it 3x. Do you know the name if you have one term versus 3x plus 7 is 2 terms. 3x squared plus 7x minus 4 is 3 terms. Those are the only 3 that get special names. 1 term, 2 terms, 3 terms. Levi, redeem yourself, buddy. 1 term, you know that saying mono, e-mono? Trimono. Monomial is the special name for a 1-termer. Binomial, bicycle, 2 wheels. Binomial is the special name for a 2-termer. And trinomial is the special name for if it has 3 terms. Definition of saying a polynomial's degree. The definition of saying the degree is telling me the largest exponent that polynomial happens to have. So if I did this one in the red circle, you would say the degree is 1. Because there's an imaginary 1 there. If I said the one in the green circle, you would say it has degree 2. You can also then give the type of polynomial by the degree. The first 4 have a special name. Now, by degree also they each have a name. Some of these names you've already used by using regression. So this one, the red circle, you should already know what that one is called by degree. Something degree 1. Something that's degree 1.
Like how many degrees is it?
No. So anything degree 1 is called linear. Do we know what things degree 2 are called? Parabola is the name of the graph.
Quadratic.
I would hope we know it's quadratic. We just did 2 chapters on it. Do we know any of the other ones in the list? We actually talked about this one in the chapter 1 when we first started the stretches and shrinks. Started with a C constant.
Yes, sir.
Something degree 3
Absolutely.
starts with a C. And degree 4 is one you might not know, but it has to do with that there's 4 quarters in a dollar.
Quad. 40.
Quartic.
I got it. Dang it.
Yeah, no. Coefficient means the number in front of any x, so what do we think the leading one would be? Biggest is not correct. Let me write one down, and then we'll see if we can guess what it is. If I gave you 4x plus 5x squared minus 12. What do we think who wants to guess Faith, what's the leading coefficient? 5 is correct. I thought you were going to say 4 and I was going to get you. It has to go with the degreed one. So it's the largest degree, which is 2. It's the leading coefficient. So it would be the leading coefficient if you put it in standard form, because standard form is from largest to smallest. If I said I have our 4 main graphs, even odd exponent versus positive coefficient, negative coefficient. If I said find how it behaves at the end, where would you think the end of a graph is? Okay, why don't I just tell you because you're not guessing correctly.
The bottom right.
What? The
Or it
bottom?
can be top right if you want.
Okay, the end is as x goes to infinity. Now, please notice that I did not say x equals infinity. You cannot equal infinity. It's just a theory that you think at some point this graph will get there. So what they're saying then is where is the end behavior is where's the y going to? And again, you won't be there, just where will you be? If x goes to infinity, where's the graph? If I went way out here to infinity,
It's never ending.
where I have to find the graph. Where is it?
Infinity.
It's way up there. So the y value, as you go way over this way, it's way up here at positive infinity. So as x goes to infinity, y goes to infinity.
Yeah.
There's another end, though, isn't there?
Yeah, the opposite.
Negative infinity. So you also would have to say,
And
as
down.
x goes to negative infinity, where's the y? Down here is where the graph is that you drew? No, it's also way up here. It's also going to infinity.
It can go down. You just have to put it on the bottom.
Let's do this. Let's just do this last one. So if we did this one and they say the end behavior. So as x goes to infinity, where's the graph? As I go out to infinity and I say I got on the x-axis and I have to find the graph, where am I? I'm way out here. Where do I have to go to find it? I got to go down. So y will be at,
Negative infinity.
and then my other end, as I go to negative infinity, where's the graph?
Positive.
Positive infinity. Those are going to be your only choices. It's just talking about negative infinity, positive infinity. Oh!
Oh, jeez, Stone.
-1.
Yep. That's like half a point.
If you take the time to read the book, I stole from the textbook. So you could find all this information in section 4.1 if you want to read it on your own. So tell me what you know about this graph as far as the exponent. Is it an even exponent or an odd exponent? Are you guessing or do you know? One arm is up and one arm is down, you know your exponent is odd. Because your odds will stay in the negative. You know, you might be x to the 7th, you might be x to the 9th, but you're definitely to a negative or to an odd exponent. Because over here, the negatives actually go to the negative. And the leading coefficient is positive because it's quadrant 1, arm is up, quadrant 3, arm is down. That's neither here nor there. I just can't believe you didn't get it right away. Okay, so do you look at the graph, left to right like we're reading a book. Did we already talk about increasing, decreasing? Oh, that's right. So we've already kind of done this part. Increasing, decreasing, I think we've done with the parabola. So we talked about this part is climbing up the hill, and then this part is climbing down the hill, and this part is back to climbing up the hill. So answering when you're greater than 0 and less than 0, what does greater than 0 mean as far as our graph is concerned?
That's increasing.
No, increasing, decreasing was different. What did greater than 0 mean?
Minimum max.
No, that was the increase because you increased to the max and then you decreased to the min. No. What does f of x stand for internationally? When you see this, you think y. So these are your y values, greater than 0. This is all the y's greater than 0. So it's like you're above the axes, you're below the axes. So it went from the zeros. So that's when you get to use the -2, the 3, and the 5. Okay, so when are you greater than 0? You have to say this purple section is greater than 0 because it's above the axes, and this purple section. Okay, so how do we say the first one? That's an in-betweener, people! -2 is less than x is less than 3, and then comma, then you do the second purple section. X is greater than 5. So this is the same vocabulary we did in the parabola chapter, where this increasing versus decreasing, I talked about climbing up the hill versus climbing down the hill. So you have to look at the section here that is increasing. So you say this section right here is climbing up the hill, and this section is climbing up the hill. So the way you write your increasing sections is anytime x is less than -2, and then anytime x is greater than 4. Those are two pieces not connected. You cannot put them into one inequality. But the decreasing section, this yellow section in the middle, climbing down the hill, is an in-betweener. So you in-betweeners, you do write together. You say it starts at -2, is less than x, which is less than 4. All right, the last thing that we already did in the parabola section that we're doing again for any poly is f of x, which stands for the y, remember, is greater than 0 versus less than 0. So y, the f of x, is greater than 0. You want to do greater than 0 are these purple sections, because you're above the axes. That section is greater than 0, positive y in that section. So the first section here is an in-betweener. So again, you say where it starts. -2 is less than x. Oh, shoot. Wait. Oh, I screwed up here. Hold on. -2 is less than x is less than 3. I screwed up in this one. Let's go back to increasing for a second. You're increasing this whole section. So not just -2, anything up to 0. Anytime you're less than 0, you're increasing. And I knew I screwed up because the numbers you use over here are not the numbers you use over here. The increasing, decreasing go from the max to the mins. And greater than 0 and less than 0 go from the zeros. So that's how I know I was wrong. As I finish and go, so I went from these zeros. It was that section. And then this also is above the axes. So then you just do comma anytime x is greater than 5. And then these two sections would be when you're less than 0. So the first one is anytime you're less than -2. And then the second one's an in-betweener. You say 3 is less than x is less than 5.